This video is for Chapter 3 for the BUIS BUIS 2100 Introduction to Information Systems course. It's entitled Data and Business Intelligence. I'm Dr. Renaud from Shawnee State University, and I'll be taking you through this brief presentation. I want to start this discussion about data and business intelligence off with a few definitions. The first definition is a database, and a database is a collection of related data. So you can think of a database as a whole bunch of data that's all kind of related. A data hierarchy is the structure of data using files, and a file you can think of as a file on your computer's hard drive is divided up into records, and then each record within the file is divided up into fields. That's kind of an old school way of storing data, but we do need to make sure you're familiar with it. A more modern way to manage data is using a database management system, or DBMS. It's an integrated software system to store and manipulate databases. We're going to talk about file data, and we're going to talk about databases, and we're going to talk about several other data related topics as we go through tonight's video lecture. There's a little kind of funny sketch over here that kind of shows how a user interfaces a database. So a user sends a query or asks the database a question using a specific query language. The database management system then goes, searches the database retrieves what was requested, and the information is then sent to the user. So you can really think of a database management system as the interface to the data. So this slide is specifically talking about ways that we access data in files. We've not yet moved into a database system, but you could imagine maybe you have a series of text files or fixed length record files sitting on your computer or on your hard drive, and these are ways we can access the files. Now, these methods, or at least the sequential method, is also how you would access data from something like a CD, or how you access data from something like a tape drive or other stream device. And you can really look at the network itself. If you're downloading a file from the internet, the file is coming as a stream that's in sequential order, which means that it's in order. Fields are in order. You read through the entire stream. You just get it. And it's often used for backups or data that doesn't change. So you create a sequential file when you create a zip file, because the zip file writes the data out in sequential order, and the only way to get the data back from the zip file is to unzip the whole thing. A random access file is stored in such a way that records can be accessed quickly, usually by their record number. And it's usually on a hard disk. Most random access files in my past experience have all been the same length record, so that if you want record 5, you know the length of the record, multiply it by the number 5, and then it tells you where to go on the hard disk to go get it. An index sequential methodology is kind of a combination. It's a sequence with an index for quick access. Stop and think about your CD, or I don't know if you all are old enough to have compact discs and put them in a CD player, but a CD is a sequential device. You read it and it reads all the way to the end all by itself, but there is an index so that you can jump to a specific location within the file and start picking up the stream from there. You can jump to a track and then pick up the rest of the data. In addition to, storing data in files and database management systems, we really need to think about ways to look at data in lots of different kind of levels of complexity. in my database class, which many of you will take, where we spend a whole semester on the material we're talking about very quickly in 1 week in this class, or one lesson in this class, um, we can view data. We create what we call a model. And a model is basically a simplification so that we can understand things. So the book uses some different terms, but I like these terms better personally. Um, the first term would be a conceptual view of data. How would a user see data at a high level? How does the end user see the data? The end user might see the data as a spreadsheet, or as a report, or kind of as this fuzzy idea of, well, the data has this, the data has this, and the data all kind of blends together. Um, and so it's a very kind of high level conceptual view of what the data is all about. Stop and then think about the logical view, which is how the data is seen by programmers. It's structured. Um, it's how the user would have to see the data to actually go in and create their queries if they're using a query language like the SQL language, which we'll talk a little bit about later. So that's a logical model, and a logical model is more complex, more closer to the real world. And then the physical model is how the data is actually stored in the file system or the database. Now, do you really need to know the physical model of the database? Maybe not. That would be something for the database administrators, for the database programmers, for the database analysts to have gotten the data from conceptual to logical into the physical model of how the data is actually stored in the system. Let's stop and think about a library. Stop and think about the public library, for instance. We can see conceptually the library is full of books. Um, you check a book out, you drop a book off. When you're done, they put it back on the shelf. It's available for somebody else. There's a lookup where you can look up a book by title and by author, and that's a really cool kind of conceptual view of a library. But when we get into the logical details of the library, the books belong on shelves and have numbers, and you can find a book by its number if you know what its number is, and you can look its number up in the index. Okay, so that's kind of a logical view, and then we would associate a library card number to the book when someone checks it out. Okay, and then we can pull up a report of all of the books that a library card has out, and vice versa. Okay, well, that's a nice logical view. Now, let's move into the more detailed physical view of the library, where they actually have the shelves and have the rooms, and books with this number through this number in this room, and books with this number and through this number are on this shelf, and the books are ordered by number and by author, and so there's a very detailed physical view of the library that, well, you if you go to the library a lot, you learn the physical view, but if you just understand the logical view, you could probably use the library okay. You'd have to have a librarian go find the book for you, but you can kind of think of database and understanding data in the various ways similarly. Most common database model that's used, the most common data format that's used in modern systems and by most of us is something called the relational model. And in the relational model, we logically kind of look at data and think about data in two-dimensional tables. And a table is made up of rows or records and columns, which are fields or attributes. So you could think of, there would be a table of customers, and there'd be a table of vendors, and there'd be a table of items, and there'd be a table of you can see how each table has one specific kind of group of, or one specific kind of type of data in it. with each row representing a different entity. So there'd be a table maybe in our student management system, well, there is, called students. And so you would be a row on the student table, and somebody else, your classmate, would be another row on the student table. And the columns in your row define you, different than the columns in the row for your classmates represent them. The relational database also contains something called metadata, or a dictionary of rows, columns, tables. And that's how the relational database works, by creating something we call metadata, or data about data. In the relational model, each row within a table has a primary key, and a primary key is a unique identifier for each row in a table, or each record in a table. So for instance, on that student table, the student ID would be a good unique identifier. For a table that contains items that we sell, maybe a unique identifier would be the UPC code or the barcode on the item. That way we can look it up in the table very quickly using its primary key. Tables have relationships. Think about the relationship between a student and an advisor. So a student has one advisor, an advisor has many students. So we use something called a foreign key, which is the primary key of one table placed on another table as an attribute. When you take the database class, we'll spend a lot of time talking about this, but I just want you to know that in the relational model, we can link two tables together. Tables are usually, and data is usually done in a format known as normal data. And normalization is a process we go through as database designers, engineers, and programmers to reduce redundant data and to make sure that related data is kind of all together in the database. There are several forms of normal: first normal, second normal, third normal, fourth normal, fifth normal, B, C, and F normal. I mean, there are lots of different definitions of it, and it's really beyond the scope of the class, other than you knowing that is a process that raw data goes through to become stored in a relational database efficiently. A relational database lets us do all kinds of things once we have the data in there. The idea of select, which is selecting a specific group of rows out of a table. We don't need to get the whole table. We can just get the rows we want. Project or project is just getting the columns we want. So we don't have to get all the columns, we just get the columns we want. Joining is the process of bringing two tables together and denormalizing, or making the data, well, joining the two tables together using their primary and foreign keys. A union is where we take two tables that are of the same format, or two sets of data that are the same format, and jam them together. Intersect is where we can take two sets of data and find the common rows or records in those two data sets. And then difference would be find all of the rows that aren't in common between the two. So all of those kinds of things can be done in a relational database as you're slicing and dicing and as you're going through your relational data. Really powerful stuff. So we've talked about some data, other types of data, relational data, but a classic database management system includes five big pieces. And the first piece is, in a DBMS, is the database engine. In the database engine, that's what actually gets the data and stores the data. It manages the files, it manages the storage, it manages the replication, it manages to make sure that a transaction is complete before it posts, and all kinds of other things. A database management system, we talked about metadata earlier. It includes a definition of the data, or data about how the data is structured. It includes some way to manipulate the data, to add, delete, modify, or query the data. And most usually that language is a language called SQL, or structured query language. A lot of database management systems include an application generation system or application generation feature, which creates apps or elements used within developing apps that uses the data definition and the data manipulation language that uses number 2 and 3 to help programmers create good data-driven applications. And then most database management systems include a database administration system that allows for DB administrators and server managers and security people to back up, recover, secure, change management, and user access. Stop and think about a database in a healthcare setting, for instance. You have a table full of patients, and each patient is listed. But we need to be sure that our database is properly configured and the software is properly written so as to ensure that personal information from one patient isn't possibly seen by a practitioner that's not supposed to see it. So that's kind of an interesting thing. Database administration, you think, well, it's just data, doing queries, writing programs. It can get pretty darn complex when you really have to stop and think about change management, because you just can't change the database willy-nilly. You've got programs that are depending upon the database. You've got to back it up, you've got to recover it, you've got to secure it, and you've got to manage all of that user access and all those user access issues. So a database management system is so much more than just storing and retrieving data. It's got all of those other features that have to be part of it to make it a functional part of an enterprise. There are some other types of common databases. Object-oriented databases use the object-oriented methodologies from programming to kind of bring objects and methods together and store them in the database. What's kind of cool with an object-oriented data model is that you may extend or inherit a type into another type. For instance, maybe you have people stored in a people collection, but then you have a customer, and a customer is a person also. So you would take the person record and extend it into the customer, but you could also take that same person and extend it into a vendor if they're a customer and a vendor. So that's kind of an interesting thing. And then distributed data. There are several distributed data models. Amazon has one called, oh gosh, my mind went blank, but Amazon has one that's really cool. There's one called MongoDB. Cassandra is Amazon's. But the great thing about a distributed database is, imagine you've got stores around the world, or imagine you've got customers around the world. You don't want them to have to go through the network back to one specific point of failure, one database. Well, imagine you've got someone in the Eastern Hemisphere, you've got someone in Australia, and to get to a database here in Columbus or to get to a database here in the U.S., their network traffic has got to bounce through satellites, and there's latency and all kinds of other issues. So big companies, and what about if the network gets cut in Columbus, then your whole business is down. So large companies like Google, Amazon, Facebook, and lots of other big entities use something called a distributed database. And a distributed database sounds just like what it is. We distribute the data across multiple data centers in multiple continents in multiple places so that we possibly don't lose it. There are three kind of ways that we do distributed data. The first data is fragmented data. Fragmented data is, we say, well, The U.S. records will store, well, we'll store every record with an even number on this server. We'll store every record with an odd number on that server. Or we'll store this group of records over here and this group of records over here and this group of records in a third place. It's kind of distributed. That's great mostly, but what happens if you need to do a query and get records from here and over here and over here? Then you've got all the network latency, and what happens if the network's down, and so there's some issues with that if you fragment the data. Now, another way to handle that is to replicate the data and create a replicated data structure where maybe you have a database here in the US, you have an exact copy of the database in Europe, and another exact copy of the database in Asia. And when a user posts an update or something is entered in one of the three data centers, it gets sent to the other data centers maybe seconds or minutes later. All three data centers are all replicated and exactly the same once they all get caught up. Well, that's kind of cool because then you've got your backups are built in, you've got everything. I mean, but you've got all your data everywhere, which gets kind of cumbersome. Think of all the data that Netflix has of all of the video streams and all of the different formats and all the shows and all of that. That's a huge database. How they get around it is by kind of doing a fragmented, replicated kind of dual model where they replicate a record across multiple data centers, but it's not replicated to every data center. So, for instance, they might have 4 copies of a movie scattered on 4 different data centers in the world. And that way, if one data center's out, we can still get to the other copies of it. But we don't have it scattered in all 20 of our data centers. So that's kind of a fragmented and replicated at the same time. And that's kind of what we mean when we say allocated. Allocated distributed data could be that we've put all the U.S. records on one server and all the German records on another server and all the French records in a server in France. Well, there we go. So we've kind of distributed our data but allocated it based upon who's using the data and who needs it the most. Most of them kind of do. Most of the big boys use kind of all 3 of those methods simultaneously in dealing with their distributed data. There's another big kind of thing that we do with data. It's called a data warehouse. And you'll hear that word used a lot, or that term used a lot. And I want to define what a data warehouse is and kind of how it works. Basically, a data warehouse, we take data from multiple sources and we bring it together for decision making and creating business intelligence. So it's not an operational database where we see live operational data. It's not a transactional database where we can see everything up to the minute. Usually a data warehouse is updated daily or weekly, or sometimes even monthly, with data from multiple sources. So we take data from your customer relationship software or your enterprise requirements planning software, or from government entities, or from vendors or customers, or I don't know. But you take all of those different data sources and they're all in a completely different format. Remember, everybody stores stuff differently because their analysis was different and they do things differently. So you take all of that various kind of data and you run it through a process known as ETL. And the process ETL stands for extract, transform, and load. So you take the CRM data from your customer relationship software, you extract it, you transform it into a new format that's your data warehouse format, and you upload it. You then download data from your HR system, your sales system, your this, your that, your government databases, your competitors catalog. I don't know. You get data from all kinds of places. You extract it, you transform it, and then you load it into this data warehouse. Data warehouses don't necessarily follow a full relational model. They're not necessarily relational because this is all about how to ask questions. We need to model the data, we need to design the data and build the data in the warehouse for question answering, not for operations. So we don't need all of the details, but we may save raw data into our warehouse. We may create summary tables of the very same data, so data may be represented multiple times. Um, and the data is not necessarily normal or updated absolutely currently. So we may just do the extract the ETL once a day, or on a batch every night at midnight we update the warehouse, or maybe once a week we update the warehouse. But this allows us to do something called OLAP, or online analytical processing of the data in the warehouse, looking for patterns and relationships. I have a client with a massive amount of sales data for the products that they sell, and I was working with that client, and I've tried to get the client to let me set up a bit of a data warehouse for them, but they're reluctant. But I'll get them to do it eventually. The question that I want them to start asking is, well, if a client buys product A, what are the top 5 products besides product A that they might buy? Okay. So if a client buys blue frisbees, what is the top 5 products kinds that will also buy? So if you've got will they buy red frisbees? Will they buy yo-yos, green yo-yos? Will they buy, what are the top 5 things they'll buy? And then ask the data warehouse, okay, what are they not buying in that top 5 list? So wouldn't it be a really cool thing as a marketing, as a salesperson, as a business person, to be able to send your salesman into your stores, your customers that are buying blue frisbees, and say, yeah, you've got blue frisbees and you do sell a lot of those, but your competitors are also selling a lot of red frisbees and green yo-yos, and you're not. Maybe I should stock some red frisbees and green yo-yos also. What do you think? Might be a good thing for you. And you see how we just upsold them a whole bunch of new stuff because we understood our data. We understood the behavior of our other customers, um, and see if that doesn't possibly transfer. It's a really kind of cool thing to dig into data warehouses and to dig into these analytical structures, and to think about them. There's another term called a data mart, which is basically a small localized data warehouse for a single enterprise or a single division or a single entity within a company. It's basically a small data warehouse called a data mart. So I said that we're creating a data warehouse for analytics and to come up with online analytical processing. Well, there are 3 kinds of analytics, and hopefully you've seen these terms other places, but I feel I really have to just say them again because they're that important. Analytics are descriptive, predictive, or prescriptive. So let's go through what those 3 words mean. Descriptive analytics are reactive. Asking the data warehouse or asking your database management system, what happened and when? When did we sell the last green frisbee? When did we sell the last bottle of Windex? When did we sell the last 50-watt light bulb? Okay, that's a descriptive. What happened and when? Who did we sell it to? How many did we sell them? How many have we sold them in the last year? Those are the kinds of questions we would ask in a descriptive. Now, the predictive analysis, analytics that we also want to do is to say, okay, try to find out what will happen. So maybe we look at a history of a customer purchasing frisbees from us. The shop over here on the corner has been buying 50 frisbees from us every October, looks like, for Christmas. They buy a couple in the spring. They buy another box in the early summer. And they've done that for years. So can we predict that they're going to buy frisbees from us next year? Can we predict what they're going to buy? Maybe they bought more last year than they bought the year before than they bought the year before. So we could maybe say, wow, there's a trend. So we can kind of predict a trend maybe. We can predict when our customers are going to want to buy our frisbees that we have in stock, or our bottle rockets, or whatever we happen to be selling in our store. So we can use our analytics to kind of make predictive analysis, to kind of make predictive guesses. And then lastly, we may use our data warehouse to come up with prescriptive analytics. And prescriptive analytics are recommended actions. Okay, we're not asking for descriptions of the past. We're not asking for predictions of the future. We're trying to figure out what our recommended actions are. Well, that would be by coming up with a descriptive or predictive analysis of a question, and then another question, and then say, well, which of the ones which of the three options should we do? Maybe we want to add a new product, or maybe we want to increase production of something. So this prescriptive analytics allows us to recommend actions, and then we can use predictive analytics to show likely outcomes for the choices of our prescriptions of what we want to do. And really cool stuff helping clients with this stuff. Another buzzword, or another thing that you'll hear a lot about data, is big data. Big data is kind of the big catch-all phrase going around in the industry. But big data means, just imagine, as computer hard drives and as computer systems and as the internet has gotten bigger and bigger and bigger, and our data collections and our data warehouses have gotten bigger and bigger and bigger, and all of our operational systems, our transaction systems have collecting more and more data, we've all of a sudden got this huge amount of data that's so voluminous that there's no way we can deal with it all. And so there are 5 V's that we need to stop and think about data, especially data when it gets to be huge. And the first V is volume. Remember, data sets continue to grow. Most businesses never throw that historical data away. So you've got lots of data, and this data just keeps getting bigger and bigger and bigger. It also comes from the second V, a variety of sources. We've talked about that. Internal sources, external sources. In an aggregate data, in a non-aggregated format. So you've got data coming in from a lot of different variety of sources or variety of systems. The velocity of the data is something else that you also need to stop and think about. Do you need the data updated immediately? Do you need it real time? Is it okay if it's just updated hourly? Is it okay if it's updated daily? So we have to look at how fast the data is arriving and how fast we can process it and understand it. We have to also look at the veracity of the data. Can we trust the data to be accurate? Is the data coming from a system that we know has some bugs and isn't always right? Do we yeah, do we have checks and balances? Do all the debits equal all the credits? So there are all kinds of veracity checks that we need to be doing to all of our data, and especially when we get into huge data sets. And then we have to look at the value of the data. Do we really care? I mean, do we need every little bitty bit of data? Or can we just save summaries of the data after a short period of time? Do we really need all of that? Is it really that important to us? So when we're dealing with data sets, and especially big data sets, I want you to keep these 5 factors in mind at all times. How big is it? Where does it come from? How fast is it arriving and needing to leave? Can we trust it? And do we really care? Volume, variety, velocity, veracity, and value. Also, when we have data sets, big data sets, and databases in general, we have to worry about some risks. There are risks to keeping this data. For instance, what happens if your database gets compromised and gets put in a competitor's hands? What happens if your database gets compromised and possibly exposes private information of your customers? Ugh, like credit card numbers and medical histories and those kinds of things. So we have to worry about the risk of privacy. We also have to look at our data and make sure that there aren't any biases in the data. For instance, maybe we're collecting data in English only, which would potentially bias against non-English speaking customers. Or maybe we're doing other kinds of things that could bias the data we're collecting, making it not as voracious, making it not as trustworthy. And another huge risk is the unethical use of data. Data could be analyzed, um, profiles created, and unscrupulous behavior can happen because of these huge data sets. Imagine the amount of data that that a company like Facebook or Google or Twitter has collected about you, your friends, your family, and everybody around you, and all the millions of users around the world. There's some huge risks to that data being used incorrectly. Um, and we always have to ask ourselves, do I really trust them? But those are questions that we as business people who have our own sets of big data have to be extremely careful about, not to be evil. Lastly, the book talks about a couple of very common tools that are used to analyze data and data sets besides a database management system. One of them is called Tableau, and it's a really wonderful program. If you want to go out to their website, you can sign up for a student. You can sign up for a student evaluation of it. It's really cool how you can visually create and visually analyze your data into charts and graphs and play what if analysis, especially beautiful graphical what if analysis. The other tool that the book publisher talks about, the book author talks about, is Microsoft's Power BI product. Um, it's a very powerful reporting system that integrates with Microsoft products and a lot of other database management systems. And the really cool thing about it is you can generate reports that users can then drill in, see the data, and then drill in and see the data, and drill in and see the data up until the point that they've gone as far as you want them to see, because you might not want a user who can see the big summary report to go into the actual customer details or not. But some users might be able to. So it's a really cool multi-dimensional uh, reporting system that lets you create drill downs and drill ups to be able to see data and to really visualize and understand the numbers and where they come from. This concludes our video on Chapter 3. If you have any questions, please contact me at jrenault@shawnee.edu. Remember, this video presentation is copyright 2021 by me, James M. Renault, PhD. All rights are reserved. Word of warning, read the book chapter. Don't rely upon this as a complete description of all of the information in the book chapter, and read the syllabus and come to office hours and ask questions if you have any. Thank you very much.